Well, hello everyone, and thanks for having me here. It's a great pleasure. So my goal today is to present to you the provenance research that we have been doing at GSL during the last couple of years. So before doing so, let me start with a little bit of a background. So what is even provenance? So provenance, you can think of it as a hypergraph. Nodes in this graph are datasets and processes. And these datasets and processes, they can be associated with metadata. For instance, datasets can be associated with a name or a size, or the processes can be associated with the CPU or the I/O cost. And this metadata can be encoded as attributes. However, it can also be encoded as relationships. For instance, you can have a user that has executed a particular process as an example. And the final thing here is that the datasets are connected through processes in this hypergraph. All right, so when we discuss about provenance, we're also discussing in the context of coarse-grained and fine-grained. Coarse-grained provenance can be at the level of event streams or tables or CSV files or files in general, but it can also be at the level of columns or column groups. Whereas fine-grained provenance is at the level of records or record groups. Provenance can also be classified as static or dynamic based on the way that it's captured. So static provenance is captured by analyzing process definitions, such as the definition of a stored procedure or the definition of a SQL script, whereas dynamic provenance is captured by analyzing the execution of a process, so the execution of a stored procedure or the execution of a SQL script. And now, of course, you may be wondering, okay, this is provenance, but why is it even important? So based on an analysis that we did over both business and academic reports, and also based on the feedback that we're getting from our customers, it is really the case that provenance is central to many different application domains, including impact analysis, root cause analysis, collaborative analytics, and so on. And applications from these different domains are used by multiple different personas within an enterprise, such as data officers, privacy officers, data producers, and consumers, and so on. I know that this is a laundry list, but it's a really important one. The main takeaway here is that, yes, provenance is there to support a very sizable market. However, in order to support all these different applications and all these different personas within an enterprise, we really need a lot of engineering and a lot of research to be done. Now, that said, in GSL, we have been focusing mainly on three key areas of provenance research: the provenance capture, provenance querying, and provenance applications. In the provenance capture area, our aim is to capture both dynamic and static provenance that I discussed before from SQL engines, data science pipelines, and code repositories. And we're trying to do so both efficiently and effectively. In the provenance querying domain, we're trying to expose both general purpose and domain-specific programming interfaces so that we can allow our users to read, write, annotate both fine-grained and coarse-grained provenance graphs. And finally, in the provenance application area, we're trying to use the captured provenance information and potentially metadata, and along with base data sometimes, in order to drive the application logic across the different application domains, including data quality, query optimization, job scheduling, semantic type inference, and so on. All right, so now, of course, throughout the years, many members of GSL have been working across these different domains and projects. However, we're also really fortunate to attract top-notch talent as GSL interns across these projects, and also collaborate with multiple product teams, mainly with Microsoft Purview, which is the main governance platform offering from Microsoft, but also Azure SQL, Scope, and Cosmos, and Synapse Analytics. Now, my goal today is to present to you some select projects from these different areas, starting from provenance capture and the main project that we have in this space, which is called OneProvenance. Now, the goal of OneProvenance is to extract coarse-grained dynamic provenance information from databases using database execution logs. And to give you a little bit of a background on why we're doing so, if you want to extract coarse-grained provenance information from databases these days, you will either use a static provenance extractor or you will use a dynamic provenance extractor. If you use a static provenance extractor, then this extractor is going to be reading the database catalog, and it's going to be reading the tables, the view definitions, the function definition, the stored procedures definitions, and so on. And it's going to be analyzing these definitions, and it's going to be extracting provenance information. By doing so, they are useful for some applications, for some governance applications, such as observability, and they're typically easy to implement because they just require access to the database catalog. However, they come with lack of runtime information, and they typically result in incomplete provenance graphs. For instance, in this example that you see here, it's impossible to know how this stored procedure is going to be operating at runtime. And also, it's impossible to know what are going to be the inputs and the output to these all select star into statements, because it's dynamic SQL. Now, on the other hand, dynamic provenance extractors, they are operating by listening to the query logs from the database that the database is generating during query execution. And by doing so, they can avoid the limitations of the static extractors. However, current dynamic provenance extractors, they are characterized by noisy outputs. For instance, in this stored procedure, the database may decide to issue queries for statistic computations as part of query optimization, in which at the end of the day may not be of interest to business users. Also, they cannot identify dependence between queries. For instance, this select star into statement, they're not going to be associated with a stored procedure dynamic copy, and this is something important for the customers. And finally, they're quite inefficient because they rely the extraction on query plans, which are quite heavy for provenance extraction purposes, as we're going to be seeing in the experiments. Now, for these reasons, we introduced OneProvenance, and OneProvenance is able to avoid the limitations of static extractors because it's a dynamic extractor. However, we also introduce a lot of smarts so that we can avoid the limitations of dynamic extractors. So we introduce filters to prune out the noise, identify dependence between queries, and also perform efficient extraction because we rely the extraction on query text as opposed to query plans. Now, I should also note that this feature, OneProvenance, is currently in public preview in Microsoft Purview, so it's in production. And if you feel free to go ahead and check it out. And also recently we published a preprint that is on archive, but more than happy to share with you later on. Right, so now I'm going to be going into the details of how OneProvenance operate, and to do so, I'm going to be using a running example where the main goal here is to append some new sales into a sales history table. So pretty simple example. So to do so, we have two stored procedures, the sync new sales stored procedures and this clean and append sales history stored procedure. The first stored procedure is, it first checks if there is a table called state sales in the database, and if it does, it deletes the table. Then it bulk inserts the new sales from the CSV file to the state sales table, and then it executes this other stored procedure, the clean and append sales history. In turn, the stored procedure is going to be either appending directly the state sales to the sales history table, or it's going to be first converting the amount of the sales based on some conversion rate, and then only appending to the sales history. And this decision is governed by an input parameter, the system version. So, and finally, because we're talking about dynamic provenance here, we're going to be executing this workflow. So we're executing the sync new sales with a parameter of 2, meaning that we're going to be appending directly the state sales to the sales history without any conversion here. All right, so now if you execute this query to the database, then the database at the backend is going to be generating a query log, which essentially is a collection of events. And in the context of Azure SQL and SQL Server, which is our focus here, these events are called text events, and they have a specific schema. As you can see here, each event has the ID of its originating activity. It comes with its event type, and here we're focusing on 4 main types. So the SQL statement started and completed, that is indicating the start and the completion of a SQL statement. And the SP statement started and SP statement completed, indicating the start and the completion of a statement that's executed as part of a stored procedure. Now, each event is also carrying the text of its originating query. And how, besides all this metadata, you can also get metadata for query execution, such as the execution time. Client connection details, such as from which application and what server a query was executed, and user information, meaning what user executed what query. And a small note here is that some of these details can be associated with some event types and not others. For instance, the execution time can only be associated with the completed events and not with the started events. And finally, we assume that the query log, these events in the query log are ordered based on the time that they were spawned, which is really the case in the query logs of Azure SQL DB and SQL Server. All right, so having that said, now I'm going to be going into how OneProvenance operates using this example. So again, we have this workflow. We're executing in the database, and as we discussed before, the database generates query logs, which is a collection of X events. And in our case, these X events are going to be stored in Azure Blob Storage in the form of XCL files. XCL files is a file format that SQL Server and Azure SQL DB is using to store these X events files, these X events. Now, OneProvenance is going to be event triggered in regular time intervals, and in production deployments, the default is every 6 hours, but this can be adjustable. And the first component of OneProvenance is the activity collector. So the activity collector is going to be reading the new XCL files that appear in the blob storage. And the first thing that it does is that it identifies the different activities that appear in these query logs. Then for each activity is going to be generating something that we call the QQ tree. So the way to think about this QQ tree is that every parent to child relationship in this tree indicates that the child has been executed as part of executing the parent. So here this insert sales history statement has been executed as part of executing the clean and append sales history store procedure, which has been executed as part of executing the sync new sales store procedure. And a small note here is that in each node, we're storing the events that this statement was originating from. And here you can see this with a little bit with the color coding. Right, so once the QQ tree has been built for its activity, then each activity, the activity collector is going to be sending these activities to the Provenance Extractor and to the runtime information extractor. The way to think about these extractors is as follows. So at the beginning, I told you that Provenance is a hypergraph. In this graph, you have processes and datasets. Here, the runtime information extractor is going to be extracting the processes and the metadata associated with these processes, whereas the Provenance extractor is going to be extracting the datasets and some of the edges of the Provenance graph. All right, so to be a little bit more specific, the runtime information extractor is going to be navigating this QQ tree that we discussed before, and it's going to be extracting entities and relationships based on our Provenance data model. Now, of course, we don't really have the time to go over the whole model, but the way to think about it is as follows. So we're extracting queries and query runs. Here, for instance, a store procedure is a query, and the executing new sales is the query run of this store procedure. And also we're extracting the queries and the query runs that has been executed as part of executing other queries and query runs. So this store procedure statement run for this insert sales history has been executed as part of executing the store procedure statement run clean and append sales history that has been executed as part of executing this sync new sales. And for each, finally, for every query run, we also associate it with a client connection so that we can keep track from what application, what server, and from what user each query was executed from. All right, so on the other side, the Provenance extractor is going to be taking the individual statements that appear in this query log, and it's going to be extracting the provenance of the individual statements. So for instance, for this insert sales history select star from state sales, it's going to be extracting that the input is the state sales table and the output is the sales history table. All right, so once these two extractors complete, they're going to be sending their outputs to the stitcher component. And the stitcher component is responsible for stitching the provenance information that we're getting from the Provenance extractor to the process entities that have been extracted from the runtime information extractor. So to see this in our example, again, we have the provenance that was extracted from the Provenance extractor. This input is the state sales and the output is the sales history. The originating query run, the statement run for this statement is this store procedure statement run. This is sales history select star from sales. However, this statement has been executed as part of executing the clean and append sales history store procedure. So the provenance is stitched to that level as well, and also to the level of the run of the store procedure. And again, it goes recursively. So this store procedure has been executed as part of executing another store procedure, so we're stitching the provenance at that level, and we're also stitching at the level of the run of the store procedure. The end result is pretty much an instantiation of our provenance data model, which at the end is sent to the uploader component, which is simply responsible for uploading this instance to the external data catalog, which in our case, it's going to be the Microsoft Purview. All right, so that was the first version of the system that we shipped with the private preview customers. And the main feedback that we got was, okay, this is a great feature. However, we want dynamic provenance from, they wanted dynamic provenance from stored procedures that are generating lots of activity, such as queries in for loops, and stored procedures that are executing during high database load. And those two cases were not supported in our first version. And also they want dynamic provenance from select few stored procedures, DTL statement types, and queries of interest. So not every possible query that may appear in your query log. So all this feedback essentially pointed us to a direction where we had to introduce filters within OneProvenance, and we'll introduce a lot of such optimizations. Here I'm going to be focusing on two of the main ones, the uninteresting connections and the loop compression. Before I do so, let me also discuss how we introduce these filters into the extraction logic. So we introduced a sim layer where you can express your filter, and then these filters are going to be injected into the different components of OneProvenance. So we are not doing the filtering at the output of OneProvenance. We're essentially doing the selection push down into the different components of OneProvenance. All right, so that said, now let's go into the different optimizations, starting from the filtering out uninteresting connections. So for the sake of an example, let's say that we have 3 client connections executed at different timestamps. So timestamp T3, T2, T1, where T3 is greater than T2 and greater than T1. So the first client connection is executing this sync new sales with a parameter of 2. The client connection 2 is executing an ad hoc select statement, and the last connection is executing sync new sales with a parameter of 1. Now, with this optimization, we can consider only connections that are executing statement of interest. And for us, the statement of interest here are going to be stored procedure executions or DDL statements. And with this, we can drop, as you can see in the example, the second client connection, because it's executing a statement that is not of interest. It's an ad hoc select statement. And the second optimization as part of this sub-optimization of this optimization is that we can keep only the connections with the latest K executions of a stored procedure. And in production deployments, we are setting K equals 1, which is the stricter version of this optimization. And in our example with this K equals 1, you can see that we're keeping only client connection 3 because it has the execution, the latest execution of sync new sales, and we're dropping the client connection 1 because it has an earlier execution of the sync new sales. And with this optimization, we saw 2 to 3 orders of magnitude improvement over OneProvenance in E2E latency of OneProvenance without any optimization, and that's in production workloads of our private preview customers. So the second optimization that I'm going to be discussing is the loop compression. And for the sake of an example, again, let's say that we have this while loop. So in this loop, we are doubling the list price of products up until the average price goes above a certain limit of $300. Now, when we execute this statement, possibly multiple iterations of this while loop are going to be taking place. As part of each iteration, multiple queries are going to get executed. And for each query, we're going to be having 2 events getting triggered, the start and the completion of the statement. Now, with this optimization, we are first detecting loops from X event logs, and apparently this is not an easy thing to do. And after we have detected these loops, then we can consider only the latest K iterations. And here again, in production deployments, we use the stricter version, which is the K equals 1, so just the latest iteration. Now, with this optimization, we saw up to 3 orders of magnitude improvement, again in production workloads of our private preview customers. And this is in comparison to OneProvenance, again, without any optimization. All right, so now I have shown you a little bit the effects of the optimizations that we have introduced. However, one question that remains is how OneProvenance compares with other engines when it comes to using the query text as opposed to using query plans. And also with respect to the logging overheads that we're adding to the database, and with respect to the latency of provenance extraction components, both in isolation and end-to-end. So I'm not going to be going over the setup for these experiments. Here I'm going to be describing only the main takeaways. So with respect to logging overhead, is really the case that logging query plans is way too expensive, even for mild transactional workloads. Whereas logging the query text that OneProvenance depends on is quite negligible, even for mild to high transactional workloads. I wouldn't say we're quite there yet if you have like very high transactional workloads. But even for high workloads, high transactional workloads, this can be negligible. Now, in terms of performance, when it comes to the different components, both in isolation and end-to-end, the main takeaways that we got was that the query text, using query text is better than using query plans, even for provenance extraction. So even if you pay all this cost for logging query plans, it's not like you're gaining something from the provenance extraction perspective. So that's the first takeaway. The second takeaway is that OneProvenance is able to scale linearly with respect to load. So for instance, here you can see in the right chart, while we're increasing the number of DPCC transactions, the OneProvenance is able to scale linearly with respect to this load. And the final takeaway is that the component latency, it really depends on the load type. So if you have analytical workloads, most of the time it's going to be going into the provenance extraction because these queries, the analytical queries are quite complex. Whereas if you have transactional workloads, most of the time is going into the construction of QQ trees because you have many small queries, short-lived queries, so which result in many QQ trees with many nodes each. All right, so just to recap on the OneProvenance, I present to you OneProvenance. OneProvenance avoids the limitation of static extractors because it's a dynamic extractor. It filters out the noise by introducing filters that it pushes down into the extraction. It also identifies dependencies between queries because it identifies and operates on these QQ trees. And finally, it performs efficient extraction because it depends on logs that have query text as opposed to query plans. And that's the main project that we have in the provenance capture domain. So now I'm going to be describing another project that we have in this domain, which is DSProvenance. And here the main goal is to extract machine learning related provenance from data science pipelines when the input is either a Python script or a notebook, where the data science is expressed in a Python script or a notebook. And to give you a little bit of background on why this type of provenance is important, so for security concerns, you may be having a data source tampering incident, and in which case you may be wondering what models have been poisoned as a result of this incident. For privacy concerns, you may be wondering what models have been built using PII data. And for fairness considerations, you may be wondering what is the model performance on specific input groups. And provenance is the type of information that can help you answer this type of questions here. All right, so now in this domain, we have been trying to build both static and dynamic extractors. At their core, both of these extractors, they are performing 10 tracking style algorithms for data flow analysis, either static or dynamic. And the data flow analysis is primarily driven by knowledge bases that we have been building that are annotating these data flows with semantics. Now here I'm going to be focusing more on the VAMSA, on the static extractor that we have. However, if you're interested, you can also discuss later on for a dynamic extractor. All right, so the way that VAMSA operates is that it reads as input the Python script. And the first thing that it does is that it compiles this script into a workflow in our in-house internal representation. This workflow is going to be input to the ML Analyzer, and the ML Analyzer is going to be annotating the nodes and the edges of this workflow with semantics that are coming from a knowledge base. The annotated workflow is then going to be input to the Provenance Tracker component that is responsible for going back and forward in this workflow so that it can identify provenance information. And this provenance information is then going to be stored in an external data catalog, such as Microsoft Purview. All right, so now I'm going to be going into the details of the different components. In order to do so, I'm going to be using a running example that's coming from this heart disease Kaggle competition. So the first thing is that we are importing some libraries and modules. And then we are reading a CSV file, this heart disease.csv file, and we're loading into a data frame. Then we're selecting a set of features by keeping all the records and projecting out the first 3 columns. We are dropping also the ID and the social security number columns. And finally, we're setting the ground truth to be the target column of the CSV file. Then we're splitting the data to train and validation sets. And then we're serializing and training a cat boost classifier model. And that's pretty much the example. Now, this Python script is first going to be input to the derivation extraction component. And the first thing that this extractor is doing is it compiles this Python script to an abstract syntax tree, which is the internal AST that Python is also using for query execution purposes. Now, once the AST is completed, then we're generating a set of provenance relationships. Here, the provenance relationships is at the level of the data flow, so not the provenance relationships that we want at the output. And these provenance relationships that we discuss here are quadruples, where each quadruple has a caller, an operation, the inputs, and the outputs. So if you focus a little bit your attention on this subgraph on the right here, on the left right here, on the bottom right here, the caller is PD, the operation is this read CSV, the input is this hard disease.csv, and the output is this train DF data frame. All right, so these are the provenance relationship. The last thing that the derivation extraction needs to do is to pretty much connect together all the provenance relationships based on inputs and outputs and form the overall workflow. Now, of course, the more complicated your Python script, the more the complication of the workflow that you can have. All right, so now this workflow is input to the ML Analyzer, and as we discussed, the responsibility of the ML Analyzer is to annotate this workflow with semantic information. It does so because we want to extract semantically meaningful provenance, right? So if you want to extract provenance that says that this model depends on this table or this CSV file, you need some way of knowing that something is a model and something is a CSV file or something is a table in this Python script. All right, so to do so, it uses 2 main building blocks. The first building block is a knowledge base of fine-grained information about ML libraries and APIs. So as an example here, you can see that if we have a fit function in the Python script that is coming from the tree module of scikit-learn, then we can deduce that the caller is a model and the inputs are features and labels, and the outputs are a trained model. All right, so that's the first building block. The second building block is an algorithm that's essentially going back and forward in this workflow to propagate the information that we extract from this knowledge base. To be a little bit more specific on how this algorithm operates, we're first finding the provenance relationships from the import operations, and we set this as a seed set. And then for each item in this seed set, we're initiating a forward TFS traversal. And in this traversal, for each provenance relationship that we encounter, we ask the knowledge base, and we are annotating the caller, the input, the output, and the operation, so the components of this provenance relationship. Now, one last thing here is if we find an annotation for an input variable, then we need to start the backward traversal to propagate this information and ask the knowledge base as needed going backward. Now, I understand that this may be a little bit complicated, but let's see this in an example. So in this example, we have this import statement that is importing this cat boost library, and we set this into the seed set. So from this, we're starting a forward DFS traversal. And by this traversal, we're finding this operation, this cat boost classifier, which is the construction of this cat boost classifier. Using our knowledge base, then we can annotate that we can deduce that the output is a model, the output variable. Then we're continuing this DFS traversal, and we find this fit function. And we're asking the knowledge base, and based on the semantics that we get from the knowledge base, we can deduce that after the execution of the fit function, the caller is a trained model, and the inputs are features and labels. So now, as we discussed before, we found an annotation for input variables. So we need to start our traversal backwards. By going backwards, we find the train the test split function. And by asking our knowledge base, because the outputs are features and labels, we can deduce that the inputs are features using the knowledge base. And then going backward, we can even find out that if we have a drop function, the knowledge base is telling us that if the output of the drop function is feature, then you can deduce that the caller is features as well. And this is pretty much how the ML analyzer operates. The result of this analyzer is essentially this workflow annotated with semantics that we get from our knowledge base. Finally, the annotated workflow is input to the provenance tracker that is responsible for extracting provenance information. So the first thing that it does is that it finds in this workflow data sources and models. So you can imagine a bipartite graph between them, and then having all the paths in the workflow that are connecting data sources to models. So that's the coarse grain information. However, we go a level deeper by identifying column level provenance. And in particular, we find columns in the data sources that have contributed to the features and labels of the model. So if you can imagine these data sources and the models in this bipartite graph, then what we have to do is to iterate on the variables that are annotated as features or labels. And then we look for operations in these paths that have modified, can modify columns. For instance, the drop functions, the ilog functions, the log, and so on. And these are a set of operations that you can find in the knowledge base that we are building. All right, so if you do that, then we can find out the set of columns from the input that are contributing to the feature set, the set of columns from the input that are not contributing to the feature set, and then finally the set of columns from the input that are contributing to the labels. And we are specifying this type of information as column level provenance information that we can store then on an external data catalog. So now experiment-wise, we have two main datasets. The first dataset is 25,000 Python notebooks that were crawled from GitHub in 2017. And the second dataset is 1.2K Python scripts from Kaggle. So in this dataset, VAMSA was able to report a machine learning model in 94% of the times, a training dataset in 86% of the times, and a feature list in 78% of the times. So the main source of error is coming essentially from the incompleteness of our knowledge base. Now, we also labeled around 300 scripts, 150 scripts from each dataset in order to compute the precision and recaller numbers that we get on the feature inclusion, and the label inclusion, the model annotation precision, and the trained dataset annotation precision. And as you can see here, across the board, the precision and recall numbers are above 90%. And again, the main source of error here is coming from the incompleteness of our knowledge graph. All right. So here I described the static extractor, VAMSA. And as I discussed before, if you want, we can also discuss about the dynamic extractor. However, one of the main things that I want to highlight here is that both of these extractors are primarily driven by our interns. The static extractor that I described here, you can also, if you're interested, you can also find a paper that we published at KDD 2020 to read more about it. And for the dynamic extractor, we recently published this Sigmod demo this year. So if you're planning to visit Seattle and Sigmod, feel free to pass by. I'm more than happy to discuss more on this. One last thing that I wanted to highlight is that one of the main contribution in this work is that we are trying to do provenance extraction using knowledge bases, right? However, these knowledge bases are constructed manually. So how do you prioritize? How do you construct this knowledge base? So to do that, we have been running a longitudinal study of 1 million GitHub notebooks, public GitHub notebooks, and internal GitHub notebooks, internal notebooks, and ML.NET pipelines. And I think Bojan at some point in this seminar also presented a version of this work. You can find the latest snapshot of our work in last year's Sigmod record. I think Bojan presented the snapshot up to 2019. So I think the insights remain kind of the same, but they're also interesting to see the size. For instance, we saw like we went from 5 million notebooks to 10 million notebooks in a year. It's just getting ridiculous. All right, so the main point of this analysis is that we're trying to analyze what users are doing, pretty much, what functions they're using, what APIs they're using, and based on the popularity of functions and APIs, we prioritize what we are introducing into the knowledge base. And by doing so, we can guarantee coverage to the degree that we see in this analysis that we're doing in this GitHub notebooks. And this is the way that we're prioritizing the knowledge base construction. All right, so these were two of the main projects that we have in the provenance capture area. Now I'm going to be moving on to describe the provenance querying area and the main project that we have in this area, which is PurviewQL. To give you a little bit of background on what PurviewQL is trying to do is to expose declarative interfaces on top of Microsoft Purview, but in reality on top of any Apache Atlas compliant data catalog. If you're familiar. So to give you a little bit of background why this is important, if you're trying to build an application on top of a governance platform like Purview, then you really need to use the Apache Atlas REST APIs to do so. And that may be fine for the most part. However, these implementations are going to be imperative. And in general, imperative specifications are very hard to implement. They're very hard to maintain and optimize, especially as the complexity of your application increases. So the proposal that we have here is to introduce PurviewQL, which exposes SQL read views and functions and T-SQL write functions, so that we can allow users to implement their logic declaratively. So as applications are declarative specifications, then they're becoming easier to maintain and optimize. And the integration with other services, such as Power BI, which is one of the most highly requested asks from customers, becomes much simpler, because at this point it's just SQL, which has connectivity with many services. All right, so to give you a little bit of background on the design of PurviewQL, so PurviewQL exposes SQL read views, a collection of read functions and a collection of write functions. So the read views are providing you access to relational encoding of all entities of a certain Atlas entity type. For instance, the Azure SQL Store Procedure Run that I was describing when we were discussing OneProvenance. So this read views is providing you access to all the entities of this certain Atlas entity type. When it comes to the read functions, we're providing a set of functions that allow you to get all the Atlas entity type, the definitions of the type system, getting the entity by given its ID, getting the lineage given its ID, doing impact analysis for an entity given its ID, and also search value with a set of keywords and a set of filters. And finally, provide you functions that allow you to read and to write entities and relationship into Purview. So let's see an actual example to understand a little bit more why this is important. So let's say that we want to update the qualified names of all ADLS and 2 file paths that were input to Power BI datasets. And this was an actual ask from a customer in production. Now, if you want to do that and you want to implement this with the Apache Atlas REST endpoints, then you need to know the semantics of at least 3 endpoints, the search endpoint, the lineage endpoint, and the bulk endpoint. You need to properly set the parameters for these endpoints, and you need to work around limitations of this endpoint. So the search endpoint is not returning, it has a limit on how many entities it returns each time. The lineage endpoint has a limit on the hops away that it returns lineage for a given entity. And the bulk endpoint has a limit on how many entities it can ingest each time you're calling it. So you need to work around all these limitations. And finally, you need to implement all this logic imperatively in Python, C#, and what have you. All right, so in contrast, if you want to implement this logic in PurviewQL, then it's as simple as a SQL statement of 10 lines of code. So here you're getting the lineage of all the Power BI datasets and fixing the input to be of type Azure Data Lake Gen 2 path. And then you're projecting your edited qualified name based on the logic that you want for the edit, and also projecting the type name, the name and the ID, the attributes and the classifications, because these are required when you're trying to do ingestion. That's going to be resulting in an update as opposed to the creation of new entities. And that's pretty much it. The whole logic is implemented in 10 lines of code. Now, if you want to see a demo of this, on the right-hand side, you see an ADLS Gen 2 path in Purview. And what we try to do here is to trim this trailing this trailing slash, which was the actual ask from the customer. Trying to do so for all the Azure Data Lake Gen 2 paths. On the left, you can see the query that I was showing you before, a little bit more verbose. Once this completes, we can refresh and we can see that we have edited the qualified name. And on the lineage view, you can see that the ADLS Gen 2 path is connected with the Power BI dataset, indicating that we actually perform an update as opposed to the creation of a new entity. Now, of course, this was just one example. Over the years, we have created many such examples, but the main takeaway here is that complex logic is becoming much easier to develop, optimize, manage, extend, and overall secure. And finally, the integration with other services becoming much simpler because it's just SQL at this point. Right, so let me conclude this area by discussing a set of open challenges that may be of interest. Here we discussed about the development, and our main proposal was to expose a declarative interface, essentially expose declarative interface on top of data catalogs that allow us to read and write provenance and metadata. However, now that we have these declarative abstractions, then the next question is how can we improve the bulk read and the bulk write performance? And if you're interested about any of those two challenges, I would be more than happy to discuss with you later on. All right, so all right, so finally, I'm going to be going into the provenance application domain, and here I'm going to be giving you some short descriptions of the provenance-aware projects that the team is trying to run. Starting from query optimization, the goal here is to use provenance both across and within systems for query optimization purposes. Of course, you can have multiple such optimizations, but some examples may be that you can push down or pull up selections and projections by looking at the provenance that you can track across systems. So that's just one example. Another example is that for query optimization purposes, you can treat a CETAS table, like a create table as select table, as a view, if you can find out that there are no updates to base tables. And this is some information that you can get from the provenance graph. So another area where the team is taking a more provenance-aware angle is job scheduling. And here the goal is to use provenance in the form of dependencies between jobs to better schedule jobs in a cluster. So dependencies of jobs here may mean that if you have job A and job B, and job B is consuming the output of job A, however, job B is scheduled 3 hours after job A, then you may be able to take a better decision and schedule it after 1 hour or 2 hours or 4 hours, depending on the dependencies of other jobs and the availability of the resources in your cluster and the potential SLAs that you may be having with customers. And this project is actually running in the Cosmos cluster for scheduling jobs in Cosmos. So another project that we are taking also a more provenance-aware angle is the semantic type inference. And to give you a little bit of a background here is that it is really the case that data catalogs these days enable you to do semantic classification of assets. So you can classify assets as PII, as Canadian passports, as social security numbers, and so on. The goal that we have here is to propagate these classifications in order to infer the semantic types of unclassified assets. So for instance, here you can see that we have an annotation that is a currency exchange. If we can propagate this annotation back and forward in this graph so that we can deduce that the output is in dollars, whereas the input is in euros. All right, so the final project that we're trying to take a more provenance-aware angle is code synthesis. And here the input is some intent expressed in some natural language. For instance, let's say we want to compute what city has the highest number of departing flights. This question in natural language is going to be input to the codex for data system that the team is building. And how the system is working is that it's going to be searching within Purview for tables related to cities, flights, and airports. It's going to be taking the provenance of these tables, and it's going to be spitting out top K programs using this information that's going to be best answering the input question. And with that, I think that concludes my talk. Thanks a lot for having me. Pleasure to be here, and more than happy to answer any of your questions.